So in the first part of today's lecture, we looked at diamagnetism, how materials which are comprised of atoms which have no magnetic moment in their ground state can acquire an induced magnetic moment due to currents that flow in the atom or the molecule, and that gives rise to this negative susceptibility and the diamagnetic response. But to understand paramagnetic materials with a positive susceptibility, it seems that we need to have a material that's comprised of atoms which have a magnetic moment in their ground state. Okay, so let's start to review what we know about angular momentum and quantum mechanics for the hydrogen atom and see if that provides a way in which we can understand how atoms can have magnetic moments in their ground state. So we're going to start with hydrogen, okay, one electron atom, which we can solve analytically, and we'll use that in the following lecture as the basis to understand multi-electron atoms. So solutions of the Schrödinger equation for the hydrogen atom will be labeled by 3 quantum numbers. Okay, so we will look for solutions that are separable. So here I've got my general wave function, which is a function of r, which is the position in 3D space. And I will try to write it as a function that depends only on the distance from the nucleus, so on the scalar coordinate r, and also an angular part, a part that doesn't depend on the radius, but depends on the longitude and latitude, if you like, theta and phi. Okay, so this function phi describes the angular dependence of the wave function. And we have these 3 quantum numbers. We have the principal quantum number n, the angular quantum number L, and the suspiciously titled magnetic quantum number ML. We might imagine that that's going to play a role very soon. Okay, let's review those. So the principal quantum number, this determines the energy of the electron level in the hydrogen atom. Okay, so if we know the n quantum number, we can work out what the energy level is. So for example, in the ground state, the lowest value n can have, in the ground state, that's n is 1, and the energy would be minus 13.6 eV. Okay, that's a Rydberg. If we go to the second level, n would be 2, the energy would be less, and they'll get closer and closer, and as n goes to infinity, the energy here goes to 0. Okay, they get closer and closer together. And we say that electrons with the same n belong to the same shell. Now the angular quantum number L, given this lowercase l here, that determines the magnitude of orbital angular momentum. So we know that angular momentum is a vector because if something rotates, it rotates about an axis in 3D space. That axis can point in different directions. And so angular momentum is a vector with 3 components. And the L quantum number determines the maximum length of that vector. And L takes values from 0 up to n minus 1. So for example, if n is 1 in the ground state, the only value that L can take is 0. And by convention, we tend to label the different values of L with S, P, D, and F. You're familiar with those from chemistry. So L is 0 is an S state. Okay. So if n is 1, this is the first shell. We have the only state we have available to us is the 1s state. And this is the n is 1, L is 0 set of quantum numbers. Now there's something interesting here, which is that if you thought about a Bohr model picture of a hydrogen atom in which the electron went round, that would be the ground state in the Bohr model. The ground state of the Schrödinger atom, which we know is somewhat closer to reality, will be the 1s, and that is L is 0. So there is actually no angular momentum in the ground state of the hydrogen atom. Okay, N is 2, the second shell. Now we can have L is 0 or L is 1. So this means 2s or 2p. When we go to the third shell, L can take any value from 0, 1 or 2, and we would say this is 3s, 3p, 3d. Okay, these will be familiar to you for how the periodic table is brought together. Now the magnetic quantum number. So ML takes integer values from minus L all the way up to L. And what this physically corresponds to is it's the component of angular momentum along a specified direction. And by convention, we call that the z direction. So Lz, the component of angular momentum along the z-axis, is ml lots of h bar. Again, it's quantized. So if we would consider, for example, the third shell, what possible values could we have? We've got n is 3, so L could be 0, and ml, no choice there, it also has to be 0, so there's one orbital with that set of quantum numbers. For n is 3, we can also have L is 1, and this would enable ml to be -1, 0, and 1, so there are 3 orbitals, 3 distinct sets of quantum numbers. And if we go to L is 2, so that's the 3D, ml can now be 5 different values from -2 all the way up to 2, so there are 5 orbitals. Now, if we were to include spin, which is not in our Schrodinger equation, but if we were to put spin in there, we double each of these numbers. So we go 2, 6, and 10. We included if we wanted to have, for example, for F, that would be 7, and so 14. And if you look at the structure of the periodic table, you've got 2 for the first two for the alkali metals and the alkali earth metals. Okay, your main block over on the right hand side, where you've got boron through to neon. Okay, there are 6 columns over there. If you look at the transition metals, okay, that's where we're filling the d orbitals. There are 10 across the states across the d orbital part of the transition metal block. And if we look at those heavier elements, the rare earths down at the bottom, where we're adding f orbitals, you'll count 14 across there, which is 7 times 2. So we can start to see how these numbers correspond to the, for example, the form of the periodic table. Okay, just a little bit about angular momentum in quantum mechanics. So, as I said, angular momentum classically is a vector. We need, if we're going to have an object and we set it spinning, it's spinning about some axis, which if we set up a coordinate system x, y, and z, we can work out its angular momentum around the x-axis, the y-axis, and the z-axis. Okay, and we can know those 3 things. In quantum mechanics, that's not possible. Okay, we can know the length of the angular momentum vector, so represented by mod L here, and we can know one of the components of the vector, so a projection onto one of the axes. And again, I said by convention, we take that to be Lz. So in the language of quantum mechanics, L squared and Lz commute, so we can measure both of them. But for example, Lz and Ly do not commute, so we can't measure them simultaneously. So if we were to take, for example, a 2p orbital, so that would have L is 1, and let's take the ML is 1 state. If we put those numbers in, we see that mod L, the length of the vector, is root 2 lots of h bar, whereas the projection on the z-axis is just h bar. So what's that really showing us? Here's my z-axis. Okay, so this is my z-axis, and my angular momentum vector cannot lie along the z-axis. Okay, so the thing cannot be rotating around the z-axis. What it must be doing is there must be, if you like, the projection of this vector onto that axis. So this length here is √2. This length is just 1. And what you can think of it as if it's precessing around. Okay, so we know nothing about its angular momentum in the x and the y directions. So we can imagine a vector that points somewhere around here. Okay, so we imagine that it's just completely undetermined. It's somewhere around here. This is completely different to our experiences of angular momentum. Okay, if you're sitting on a desk chair, something that can spin around, if you spin yourself around, you're kind of sure about what axis you're spinning about. You can definitely spin around the x-axis. Okay. Well, why is that? You're in the classical limit. Okay. So angular momentum, so a point mass orbiting is mr². Let's imagine you had a kilogram mass on the end of a 1 meter string. Okay, not implausible, and you're spinning that round. That would mean that and you spin it round at say one meter per 1 radian per second. So your angular momentum I will be the order of 1. Okay. What is h bar? H bar is the order of 10 to the minus 34. So macroscopic angular momentum is a huge number of h bar. Okay, it might be, if you spin your desk chair, it might be the order of 10 to the 34 lots of h bar. Okay, so L is really big. Okay, it's really, really big. And once L is so big, it means that L plus 1 is essentially L. And so the square root of L plus 1 is just L. Okay, so when angular momentum is macroscopically sized, there is a very definite axis of rotation. Okay, so the axis of rotation is well defined for classical objects, but for these very light objects, the axis of rotation is not well defined. Okay, so we just know the projection onto one axis. Okay, so let's do a bit of an estimate. What I'd like to know is if I've got an electron with angular momentum in an atom, what is its magnetic moment? So I'm going to do a fairly classic sort of what we might call a semi-classical calculation. And happily it will agree with if I did a more exact quantum mechanical calculation, but I think this gives us the feel of what is actually going on. Okay, so magnetic moment M is equal to the current times the cross-sectional area. Let's assume that the electron is in a circular orbit at radius a. So in other words, that's telling me that the cross-sectional area A will be equal to pi a squared. Okay, and the current is just defined as the charge passing a point per unit time. So in other words, I is equal to the electronic charge divided by the time for one orbit. Okay, but the time for one orbit is just going to be, well, it's the distance it needs to travel over the velocity. So this is just 2 pi a over v. Okay, so this is the sum of circumference and this is the speed. Okay, let's pop that in. So if we put this in, this will be E, V comes on the top, and this is 2 pi A. Now electrons are negative, and to make things a little bit simpler then, I will write this as minus mod E V over 2 pi A. Okay, so we can get a little bit confused about whether E is meant to be positive or negative, but if I write it like this will make it clear. Okay, but we know that angular momentum is quantized. Okay, so in other words, the mass on the electron times VA. So this is mass, this is angular velocity. Okay, that will equal ml. Need to be a little bit careful with my e's, don't I? So just let me doctor that. There we go. The e's and the l's are different. So angular momentum is quantized. Okay, so the mass times the angular speed will give me an integer ml, lots of h bar. So this implies that the velocity v is equal to ml h bar over me a. Okay, right, I can go back to my definition. So the magnetic moment equaled IA, and that's going to be equal to minus mod E over 2 pi A times V, well that's ml h bar over me A, and we need to dot that with the area. Okay, so that's then minus mod E h bar over 2 me times ml. In other words, m equals minus something I'm going to call mu b ml, where mu b is equal to mod E h bar over 2 me, and this is what's known as the Bohr magneton. Okay, so what this is telling us is that the natural unit of magnetic moment is the Bohr magneton. So an electron that has h bar angular momentum has the Bohr magneton units of magnetic moment. Okay, and the minus sign here is coming because the electron is negatively charged. Okay, so the minus sign is because of that. Okay, so that's our derivation. I said it's a rough sketch using a semi-classical argument, but it does give us essentially the correct answer that would agree with a more quantum mechanical calculation. So to summarize, the Bohr magneton is the elemental unit of orbital angular momentum in an atom. Okay, there we have its value. This would be present in any table of contents that you'd be given. And so if we now wanted to find the magnetic moment, we can know the length, the magnitude of the magnetic moment, m. Okay, it's just given by l plus 1, lots of mu b. And if we want to know the projection of the magnetic moment onto a particular direction, which we call the z-axis, then it's given by minus mu b ml. And remember that the minus sign is due to electron negative charge. Okay. Now, why is this important? Well, remember that the energy of a magnetic moment in a external field is E is equal to minus m dot B, where B0 is the applied magnetic field. If we say that B0 is in the Z direction, we're free to do that. You see that we only need the Z component. We only need the projected component of the magnetic moment. Okay, so and in that case, we would find that the energy is just given by the ball magneton, the value of the applied field, and ml, the magnetic quantum number. So let's have a look. So there's something called the Zeeman effect. If we consider, so we've got the hydrogen atom. Okay, let's have a go at drawing this. So we will first look at the case of no magnetic field. So let me draw some energy levels. Okay, so in a multi-electron atom, the S levels and the P levels will be at different energies, and we would get something like this. Okay, two different energy levels, and we could imagine an electron being able to drop down from one to the other, and that would give rise in a spectrum to a single line. Okay, where the energy of this line corresponds to this energy difference. Now, what would happen in a magnetic field? Well, what would happen is the S level will stay the same, but the P state will split because of the energy that we've just talked about. So the ML is 0 will be unchanged. Okay, but the ML equal 1 level and the ML equals minus 1 level, okay, they will be at different energies. Okay, so what will that do for the spectrum? Well, I can now get three different transitions. I can get this one down to here, I can get this level down to here, and I'll get this level down to here. So what we would find in our spectrum is one line at the same frequency, but one line to one side and one line to the other side. We get three lines. So this is something that is not accounted for in the Bohr atom, which is that under magnetic fields, you find that the levels in the spectrum, the lines in the spectrum are split. Okay, so this is direct consequence of the Zeeman splitting and the magnetic moments of those different energy levels. Okay. So the last thing we need to consider is the spin magnetic moment. Okay, so to fully describe the quantum state of the electron in the atom, we need to have two further quantum numbers, and these are associated with the spin of the electron. Now, first of all, just a comment about spin. Spin is a form of angular momentum. We know that because it can interact with the orbital angular momentum that we're familiar with. Okay, and they can combine together to form a total angular momentum, and that total angular momentum is conserved. Okay, but whereas the orbital angular momentum of an electron going round in a physical loop, the one that we've talked about on the previous slide, that is the exact same type of angular momentum that you have when you spin round on a desk chair or on a merry-go-round. Okay. Spin, however, doesn't have that kind of direct interpretation. It isn't that the electron is actually spinning. Spin is just a word that we use. So it's difficult to describe simply because there is no macroscopic manifestation of this. So you can't look at a macroscopic body and say, that has spin, because it doesn't. Okay, it is a form of angular momentum, but it's not a form of angular momentum that we're used to observing. So in that sense, it becomes a little bit mathematical to describe it without a physical picture, but it is important to bear in mind that it's a type of angular momentum. Okay, so for an electron, we have two quantum numbers. We have S. However, for an electron, that's fixed. This wouldn't be the case for nuclei. Nuclei have spin as well, and they can have spin 3 halves, 5 halves, 7 halves, all sorts of different things. There it's a little more complicated, but for electrons, they're just fixed to having S is equal to a half. So we often even don't bother talking about the S quantum number. But the MS quantum number, the projection onto an axis, is simply plus or minus a half. And the same formulas apply. So we can know the length of the spin vector, the length of this angular momentum vector. It's given by s plus 1 square rooted, lots of h bar. And we know the projection onto an axis, again by convention, the z-axis. So sz is equal to the ms quantum number, lots of h bar. This means for an electron, the magnitude of the spin is root 3 over 2 h bar, that's fixed. And the projection onto z is simply plus or minus h bar over 2. Now, you might think that we could just convert from the angular momentum directly into the magnetic moment in the same way that we saw we could do for the orbital angular momentum. But there's a bit of a catch in this. We need what's known as a G factor. So a G factor is what translates between the angular momentum and the magnetic moment. For the orbital case, the G factor was just 1, so we didn't bother talking about it. But in this case, it turns out that it's slightly bigger than 2. So the magnetic moment down here is mu b ms, which is either plus or minus a half, gs, which is this number here, slightly bigger than 2, and there's also a minus sign. So two things to comment on here. It's not exactly 2, it's slightly bigger than 2. This is predicted by something called quantum electrodynamics, QED. You might have heard about people like Richard Feynman, who won the Nobel Prize for working on one of the people that worked on quantum electrodynamics. It's one of the most successful theories of predicting the property of matter on a small scale. And it predicts the value of GS to a considerable number of decimal places, and that's been very carefully verified by experiment. So it's slightly bigger than 2. However, it is sufficient in terms of dealing with materials to just take it to be equal to 2. And so for everything that we're going to do, we're going to take GS, the G factor associated with the spin of the electron, to be integer 2. Okay, it's not going to make any measurable difference for us. It does have some consequences, but not really for magnetism in materials. So that's the first thing. The second thing to note is the minus sign, and the minus sign is predicted by Dirac's equation. That's the relativistic version of the Schrödinger equation. So again, that's something that's predicted, and it means that the magnetic moment is in the opposite direction to the spin angular momentum. So if the spin points up, the magnetic moment of that state is actually pointing in the opposite direction. Okay. So just something to bear in mind.